Tonight's talk is using reliability analysis and probabilistic risk assessment to achieve lifecycle seaworthiness on the Hobart-Class guided missile destroyer by Daniel Johnstone from AMOG Consulting. Daniel is a principal engineer with AMOG and is currently the team lead for the systems and safety engineering team. He joined AMOG in 2011 and has worked in all of AMOG's engineering teams over the years, gaining experience in a variety of engineering skills, such as structural analysis, vessel motions, vortex-induced vibrations, fatigue analysis, numerical simulation work, forensic failure, and legal investigative work. So I think he's not a naval architect, but obviously has a lot of naval architecture relevant experience there. So he could be an honorary member. Daniel moved into the systems and safety engineering team in 2017 and has been involved in the defence sector for the last 5 years. He's been working with various SPOs, such as MCD SPO and DDG SPO, to deliver a variety of systems engineering and safety engineering outcomes, such as hazard analysis reports, safety case reports, probabilistic risk assessments, reliability analyses, and more. So I'm going to hand over to Daniel.
All right, welcome. Thanks very much for inviting me to come and present. Really appreciate the opportunity. And hopefully everyone will find this at least somewhat interesting. The title is a bit of a mouthful: using reliability analysis and probabilistic risk assessment to achieve lifecycle seaworthiness on the Hobart-Class guided missile destroyer. There's a lot of keywords in there and jargon, but hopefully by the end of the presentation, it all makes sense and it will have been an interesting one. Oh, and now it's not working. It was so reliable before. Okay, cool. All right, I'm just going to start by giving you a little bit of initial context about defence acquisition projects. Generally in the defence industry, I've been told, and this comes from the Director General at NCB. He threw out these statistics at last year's IMC conference. He said 1/3 of all of the costs of any acquisition project goes towards paperwork. So like assurance documents and design stuff and ILS documents. And actually only 10% of all that stuff ends up being used in the in-service life through the life of the project once it's put into service, which is staggering, pretty alarming. And I reckon that there's a lot of room for improvement there. And one of the things I'm going to try and talk to you today about is how we can sort of use all of that work that's done a bit more wisely and actually put it to good effect in the sustainment of the platform, whatever it might be. I'm going to talk a lot as well about the Hobart-Class DDG destroyer. I know some people in the room will know it really well, but for anyone who might not know too much about it, it's the big new destroyer that the Navy's just purchased. It's been in the works for probably the last 10, 15 years. Designed by Navantia, built by the Australian Shipbuilding Corporation. It's about 150 metres long, about 18.5 metres wide, and it has lots of vertical launch silos at the front, about 48 of them to launch lots of missiles. It used to be called the Air Warfare Destroyer, so that's kind of gives you an idea of what it's designed to do. The Navy's got 3 of them and they cost $9 billion. So just going back to what I just said, if they had said, we don't want any paperwork at all, just give us the vessels, they could have had 4. But yeah, also in accordance with that, then I suppose, you know, 900 or almost $1 billion was spent on paperwork that wasn't used, you know, well, most of it wasn't used. So what we're trying to do is we're trying to get some synergy going and actually use all of that information and the analysis that's been done to inform the safety case and to inform the seaworthiness case. The safety case is obviously focused a lot on risk, but there's also risk to capability, which is a lot of what the seaworthiness case is about. You've probably all heard of phrases like this. Oh, the pointer doesn't work, but the phrases like this, you know, critical ship system X must have an availability of 99.0% across the system life cycle. We're going to try and investigate what that actually means and how to actually achieve that today. During that acquisition phase, like I said, all that ILS documentation, such as FAMICAs and RCM analysis, is trying to confirm those requirements. It's trying to prove that that's what will be achieved. But we're going to try and increase the fidelity of the models by using the method I'm going to talk through today. And we're also going to try and make those linkages and try and build an argument that the ship is safe and that the ship is seaworthy. And of course, the end goal is to develop an analysis product that's capable of delivering actionable data to the in-service decision makers about how changes in the way they operate it will actually affect that high-level goal or requirement. Okay, so here's today's agenda. I'll give a bit of an introduction. I've already given a bit of context. I'll talk about the methodology that we used, which is largely around RBD models, but there's also fault and event trees to do some semi-quantitative probabilistic risk analysis. And then I'm just going to use a whole bunch of results and inputs from the case study, which is the DDG, which is the one we've been working on the last 3 years. And then I'll try and give some conclusions. Okay, so I'm sure that this is probably a fairly intuitive graph, but this is sort of where I'll start. The genesis of this work was basically a question from BAE, who are the lifecycle manager of the DDG. And their question was, how do we develop a defendable maintenance budget? How do we actually defend the money that we're asking the government for through sustainment? And really the question is, how much maintenance do we actually want to do? Because there is some diminishing returns. There is a point of inflection there, We obviously intuitively spend more money on maintenance and the availability of a system or a function will go up. But then at some point we're over-maintaining the system. We might actually be introducing more errors than we need to. And also we're going to be taking the system offline a lot to keep doing all this extra maintenance, which affects the availability negatively. So from this sort of start point, BAE and AMOG sort of partnered together to develop a decision support environment where systems-based analysis could capture the importance of maintenance and operational regimes and link it all back to the framework that Navy's familiar with, the safety case and the seaworthiness case. And the idea with this decision support environment is to be able to interactively ask questions and get answers in a relatively quick fashion. So, for example, if the CMR of the DDG SPO, or sorry, the person who's in charge of the DDGs asks a question, we have an operational need to increase our deployment duration. We want to go out for 150 days instead of 100 days. How's it going to affect the probabilities of our different systems being available? How's it going to affect the maintenance budget? Are we going to be wearing things out too quickly? We have an operational need to use our platform more overtime than expected due to unforeseen layup or upgrade, or maybe due to resource constraints, certain maintenance activities can't be performed. So what should we be prioritising and what will have a long-term effect or a short-term effect? These are the sorts of questions that we're setting out to answer when we build this sort of decision support environment. Okay, so I've told you enough about sort of the what and the why. I'll try and talk to you now about how we're going to do this. The first thing that we do in this methodology that we're going to use, we define the context and the function. When I say function, I mean like an operational effect that you'd find in the seaworthiness case, right? There's different sort of capabilities and there's different functions that you must be able to achieve, and those functions might have many different systems that need to perform, and only certain parts of those systems might need to perform. So there's a level of criticality that needs to be taken into account. Certain components are less critical than others and can fail, and the function will still be available. So we define that first. Then we build a big reliability block diagram model, RBD model. And that's just a big, a big model right down to the lowest replaceable units of every critical system that we've identified that's critical to delivering the function. We establish the failure data. Now this is pretty tricky. This requires a bit of expertise, I feel, from people with good experience. A lot of the data does come from industry sources, so REAC, OREDA, but some of the data comes from manufacturers of specific equipment if we have that data available, and sometimes just engineering judgment is used when there's nothing else. And then we go to the operational and the maintenance regimes. So the DDG has a particular phasing that it will use throughout its life. So there might be a 10-year life cycle, and within that 10 years they've got lots and lots of planned periods of maintenance, planned periods where it will be intermittently at sea but still be around one of the naval bases, and then they will have planned deployments, once or maybe twice a year. It will go out for quite a long time, maybe 30, 60, 90, 120 days. So we're going to put all of that information into this model that we're building, and the maintenance activities. We're also going to look at all of the standard activity lists, all of the maintenance activities that go along with every critical component. That's all going to be put into this numerical model that we're going to simulate. And we're going to put all of the operational and maintenance constraints on that too. So obviously certain tasks can be performed by naval personnel when it's out at sea, but many other tasks can only be performed by an external contractor, and that can only be done when it's alongside. So we're going to take all that into account and put that into the model, and then we're going to simulate the model, and we're going to simulate it to get out availability results through time. And the way we simulate it is using Monte Carlo. So basically just run thousands of simulations and take averages of its performance. And then finally, and this is the part where we really link it back to the seaworthiness case and to the safety case, we're going to put it into fault trees and event trees to see how those availabilities will play out against safety outcomes or against, capability seaworthiness outcomes. Okay, I'm going to try and just focus though, particularly on these three bits. So the building of the actual model, the operational and maintenance constraint logic, and then the fault tree stuff. Because there's probably a lot of stuff that I could talk about today, but I've only got 40 minutes or less than that, and I want to try and give you something that's interesting that gives you a flavour of the whole thing. So that's what I've decided to show you a bit about. Okay, so we're building RBD models. We take into account all those systems that I said are, say, for a particular function, absolutely critical, and we build them, and we take into account redundancy by putting in parallel systems, or if there's no redundancy, obviously some systems will be in series. And within that, there's a little plus symbol. Within that, there's the underlying architecture of the system. There will be right down to the lowest replaceable units. Once the system architecture is defined, we can place different attributes on each block. So that includes the failure distribution and the mean time to failure, MTTF, and the mean time to repair as well, which is associated with the different maintenance activities. We'll also put the utilization on each component. So for different phases in the life cycle, the components will be under different loads, basically, under different utilizations. You go out to sea and you run the diesel generators really hard, but when you're alongside or when you're intermittently at sea, you might not run them as hard. Yeah, I already said we're going to put all the maintenance activities onto those blocks or the sub blocks. And we're also going to specify the resources that are required. And that will be really important later because we're going to keep track of all the hours that are spent doing maintenance, whether they're from naval personnel or from external personnel. And that will be a proxy to cost somewhat. Okay, hopefully I'm not going too fast. There's also the operational and maintenance logistics constraints. So we've got these phases here, right? I've just stated these 4 high-level phases. So you've got deployments, intermittent sea periods, upkeep, and then one big group of things which we've just called other. And certain things can be performed by the ship staff, so the organic maintenance tasks, and certain things can't be. They must be performed by external maintainers, and they can only be performed when the ship is maybe in an upkeep period, or some tasks, corrective maintenance, can be performed when the ship is intermittently at sea, because it's very close to being at a base. They can bring it back to be alongside to do that maintenance. For the work we did for the DDG, we developed a hypothetical usage and upkeep cycle that was really closely aligned to how the DDGs might really operate. I think I've said everything there. Okay. Okay, and then that last bit of the tree that I was showing you, the fault and event trees, how this actually plugs in. So we've got that reliability model and we've simulated it thousands of times and we get results of availability, and they're plugged into our fault and event trees, which we've built. Which will have all these different sort of controls and equipment items along the top. And there will have been a fault tree here, which tries to semi-quantify the frequency on an annualized basis of a particular event occurring. We're talking about like a hazardous event, a mishap. So in this case, it's about loss of containment of diesel fuel. And there's different ways that can happen. But the high level event is the loss of containment of diesel fuel. And this event tree is how that will play out, and the different systems that we're relying on to, say, put a potential fire out if it was to start, or to detect it, or to do X, Y, Z, to reduce the severity of the outcomes. Sorry, to reduce the likelihood that severe outcomes occur. Does that make sense? Okay. All right, I'll move on to the case study because I reckon this stuff's pretty interesting. You can see how we've approached the building of the models. So I'll spend some time looking at this. This is sort of the first number that probably jumps out at you. This is a high level functional availability for scenario 0. What's scenario 0? Scenario 0 is sort of the baseline model. You know, this is what we expect the DDG to do if everything is as we plan to do it. And we will use this baseline to continually compare hypothetical scenarios where we might change certain things. So this baseline is what DDG is planning to do, but if they're interested, if the decision makers say, hey, what happens if we take the boat out for 150 days instead of 100 days, then we will simulate something and we'll call that scenario 1 or scenario 50, and we'll compare it to the baseline every time to see the difference in cost and you know, the hours on maintenance and also the availability results. The pleasing thing for us was that once we had finally built our, you know, revision 0 baseline model after many drafts and trying to iterate to something that made sense, that was accurate, the comparison with the urgent defect data that we had access to was really quite strong. We found, and let me just read this here, we found that the model predicted that the systems that we were looking at would fail approximately 1.5 times more than what's actually being measured. And that's pretty good because given that the platform's in the early stages of its life, putting aside some infant mortality that might occur with some components, generally speaking, that probably makes complete sense because as parts wear out, there will be lots of parts which do wear out, which are prone to wear out, and therefore the distributions that we're using to model them will have a wear out curve. You know, those parts will in real life not fail as quickly as we've predicted here. So yeah, we thought that that was quite pleasing because I don't know if anyone has a lot of experience building reliability models, but sometimes you can get results that are just wildly wrong. And so at least not only are we on the right order of magnitude, but we're actually pretty close. So that was pleasing. Okay, I'll talk to you a little bit about these numbers here. So the headline number is obviously the functional availability. And that is an average functional availability of one particular function on the DDG. So it might be power generation or the HVAC system supplying ventilation, say, to the compartment. That one function across the entire lifespan of the DDG, that's the functional availability. But keep in mind that that's an average, and I'll come back to why that's more interesting later. The next thing we can see here is the man hours spent. So you can see here, this is the organic corrective maintenance. This is the organic condition-based maintenance, and this is organic preventative maintenance. So corrective maintenance is obviously about if something fails and we need to fix it. We only know that it failed because it's failed and now the system's offline, so we need to fix it. Organic condition-based maintenance, that's about when we've done an inspection and we realize that it's wearing out and we need to fix it. That's when we do that. And then there's obviously planned preventative maintenance, which is, you know, all the 6-month servicing, 12-month servicing, 24-month servicing, all the planned maintenance that is in the schedule that's going to happen. So you can see here straight away, the thing that jumps out to me is there's lots of hours for external contractors to do preventative maintenance. That's when it goes in for a big long upkeep for a number of months. And then there's also quite a bit of corrective maintenance that's going on. So naval personnel are running around the ship fixing things for this particular system annually. These are annual numbers in hours. I should have written that somewhere, sorry. Yeah, the naval personnel are running around fixing things that go wrong. They're not doing a lot of condition-based maintenance and they're doing a bit of planned maintenance. These are model numbers. These are modeled numbers. There's only been a few years, I think there's probably only been 7 or 8 ship years because the first DDG was delivered, I think, in 2017. And then the next one was delivered, I think, in 2018 or 2019. So we don't have a lot of data yet to compare really well and get a really good feel for how accurate these numbers are. I mean, BAE said on the surface of it that it looks reasonable. But yeah, these are modeled numbers. And they're modeled numbers for a hypothetical system. I haven't given you the details of what the system is because I'm trying to keep it generic. All right, so the other thing that the modeling will tell us is obviously, you know, key contributors to downtime. That's quite useful because it enables us to sort of see a snapshot of, what are the leading causes of the failures. So that way we can sort of target our maintenance strategies a bit more effectively and try and maintain the system components that are more likely to fail more effectively. All right, this is a very typical sort of a graph that you'll see lots of. This is a time series graph. So we've got right from the start, the first year, this is year 1, January, July, then year 2, year 3, all the way through to year 10. So there's 10 years. And you can see here for this particular hypothetical baseline scenario, we had 10 deployments, we had 8 deployments, approximately 1 every year, but with a major service in year 5 and a major service in year 10, where it didn't actually go to sea. You can see, so those deployments there, those yellow bars, you can see that the availability of this particular system and its subsystems drops right off during deployment. Why is that? The answer is it's a cumulative probability, and what's going on is if things break out at sea and they can't be fixed by an external maintainer, then they're offline and that system is offline. Its capability is lost. So you can understand how across many thousands of simulations, and we're averaging here, we're working out that as you are out on deployment, the probability or the availability of this system, which actually means the probability that it is available on demand, is going down from 100% when you leave the port on day 1, right down to as low as, in the 80s on day 100 of deployment. So going back to what I said before, remember that high level number where we ticked the box and met the requirement that was in the contract of this particular system or function being 99.3% available. Yes, we've ticked that, but actually the thing that's probably the most important is its performance in deployment. And you can see that that's definitely not an average of 99.3%. Okay. The devil's in the detail. Another thing that's important in all the modeling that we're doing is the definition of the capability states. So every functional capability that we're talking about here, we've categorized it into 3 states: a full capability, i.e. everything's working; a degraded capability, lots of things are starting to fail and go wrong, but the key functionality is still available. We can still do the thing that we need to do. And then finally, this sort of return to port criteria. This is where it's just, we've had so many failures of critical components and so many failures of even non-critical components that we just can't sustain the capability anymore at sea and we must return to the port. Okay. This is sort of now an example deployment. You can see through time here, I've just sort of put these percentages, percentage of the deployment completed. So this might be a few weeks in, few months, or this might be, say, 14 days, 25 days, 50 days, 75 days, and 100 days of a 100-day deployment. And you can see how the full capability drops right off. The degraded capability, obviously, is kind of the inverse of that right now because the return to port probability is very low. But then this sort of creeps up. And by the end of deployment, you've sort of got a 50-50 chance of being in a degraded state. And then finally, yeah, that return to port criteria creeps right up. And by the end of deployment, you've got a 12% chance that you have to return to port because this capability is no longer available and it's a critical capability of the ship. And that is just sort of a graphical representation of what I just talked you through. Just interesting to note here, we had a commander who had spent a lot of time in charge of one of the vessels, and he said actually that his anecdotal experience supported this because he thought that somewhere around day 70, he was saying that it seems to sort of be a 50-50 chance to whether or not you've got full capability anymore or not. So yeah, this is sort of the typical behavior that I expect though. Okay, so now we get to the interesting part. Now we've got this model and we've got the baseline and we've got sort of a baseline level of performance that we've quantified now. Now we're going to put hypothetical scenarios into the big model and come out with their results and compare them to the baseline. So some of the different scenarios that we typically assess when we were assessing various ship critical systems and functions. Scenario 1, which is all about extended deployments. This came from the CMR and he wanted to know what's the additional risk to personnel he's exposing the personnel to by operating the vessel for longer. And he also, of course, wanted to understand if it would reduce the overall capability across the life cycle. Scenario 2 was all about distributing extra days at sea. So this might occur for a number of reasons, maybe an operational need, or perhaps because one of the 3 DDGs is in for unexpected maintenance. So, and maybe it's expected maintenance. I happen to know, and we were just talking about it before actually, the DDGs are going to be going in for a major upgrade sometime in the next few years. And when each one is being upgraded, it will be offline for quite a while. And therefore, there will probably be a requirement for the other 2 DDGs to have more time at sea. So we're going to push them harder to try and make up for the fact that we're missing one. Scenario 3 focused on an optimized maintenance schedule. So that was using some analysis that other people had done. They had done some FAMICAs and some RCMs, and they had decided that certain activities should be done and certain activities shouldn't be done. And we simulated, well, what will the result be of all of their recommendations, basically? And we're going to compare that to the baseline. Okay, so here's the high-level results again, now for the 3 different scenarios against the baseline. The first thing that jumps out at me is that if we're just looking for functional availability, the FAMICA recommendations look very good. You know, we're going to do those FAMICA recommendations and increase the overall availability. Whereas scenario 1, that extended deployment, doesn't look that good. But of course, that's the result, because we've pushed the vessel, we've put it out at sea for longer, and so the functional availability went down much lower because it was out for much longer. You can also see here all the hours of maintenance that are being done and compare them. And this, like I said before, it's sort of a proxy for the cost, isn't it? If we do these FAMICA recommendations here, you can see that the external preventative maintenance hours go down quite a bit. So that might be a good way to save money. But the catch is that the organic maintenance went right up. And so I don't know if the Navy would be very happy with us suggesting that they, you know, spend 17 times longer maintaining a few systems and doing a few FAMICA recommendations. So again, the model will be very useful to dive into the detail there and find out, all right, well, what systems, what changes are these recommendations really making? And maybe we'll sort them, we'll order them based on their level of impact. And we might only do the top 5 recommendations because they'll give us a good result without maybe bumping this up as much. That's the sort of thing that hopefully this decision support environment can do. Okay, and here's that functional comparison across the 3 different scenarios compared against the baseline. Now, this is a pretty hard graph to see, actually. I'm sorry. I probably should have zoomed in on just a portion of it. But you can sort of see, you know, here's scenario 1 where we have extended deployments. There's a couple of really extended deployments here where they've really pushed the system way further because they've had the vessel out for, you know, almost twice as long, and that's how far down it went. That might be palatable, and that might be acceptable, but previously, I don't think that there was really a good way of quantifying it, or at least trying to quantify it. It was just sort of, you know, see what happens. So at least this way, we can sort of mathematically make an argument for or against certain scenarios. And then the other thing that this obviously then feeds into, remember how I showed you the fault trees and the event trees before? They feed into the safety and the capability results, which ultimately feeds into the safety case and the seaworthiness case. So you can plot out different scenarios and see how they actually land on the risk matrix. There are actually, you know, quantities to these likelihoods, and there are actually some quantities to these consequences. If we're talking about safety to personnel, for instance, you know, it's whether or not 1 person dies or 10 people are injured such that they need to go to hospital, or whether or not, you know, 10 people die, etc. So we've put all that information into this, and we're coming out with results that we can actually try and plot on this graph. And at least in my very limited experience and exposure to the defense industry, I hadn't really ever seen this happen, where people had actually come with quantified results and tried to plot them on this sort of qualitative matrix. So this was kind of an exciting conclusion, and hopefully we added some value by doing this. But so basically what I'm showing here is that, you know, the deployment capability risk profile for, say, the first 30 days versus the last 30 days for a particular system changes by this much, you know. Does this make sense? Does this graph make sense to people? So you've got, I should have explained the axis. You've got likelihoods here, you know, rare, improbable, occasional, and you've got the consequence. And basically this is trying to relate your capability that you have. So it might be, say, that we can supply power to the safety critical functions on the ship, right? Or the safety critical systems on the ship. And here is, you know, those safety critical systems are not available. So they will lead to critical outcomes. People might die. And you can see here how the risk of that happening increases as you go on deployment. You know, the first 30 days of deployment, you're down here, whereas in the last 30 days of deployment, you've started to creep up to here because the probability of those critical systems has gone down, and therefore the safety risk has gone up now that when you need that system, it won't be available. Does that make sense? Cool. Okay. I'm kind of at the end here. I seem to have rushed through, so that's fine. Yeah, conclusion. So we've developed, we believe, a high fidelity set of RBD models for select systems of the DDG, the critical ones. We've developed these models and then we've simulated them, and we've shown that they have pretty good agreement with the measured rates that we're seeing on the DDG. So we've built some confidence in these models. And now these models are enabling us to interrogate different aspects of how the DDG is operated, simulate different scenarios, and actually get some actionable data around that. So then decision makers can know, you know, an estimate of the quantity of the effect of those decisions. And yeah, the models can provide some quantitative basis for changes to the maintenance budgets and also the operational and maintenance regimes with a cost benefit analysis. So that's sort of where this is all headed.